Welcome everybody once again. So this is our fifth class for module 3 and we are studying about measuring devices. So in our syllabus we have four. In this module 3 we have to study about venturi meter, orifice meter, pitot tube and orifice. So in the last class I told you orifice is a measuring device. Actually orifice is not a measuring device, it is a part of your tank. Part of the tank where the water is flowing or where the liquid is flowing. Now, see these three, venturi meters, orifice meter and pitot tube are measuring devices. They are some external devices used for measuring the velocity of a flow or rate of flow. Now, last class we saw about venturi meter and orifice meter, and these both are used to determine the rate of flow of liquid flowing through a tube, flowing through a pipe, not a tube, it's flowing through a pipe. Now, today we are going to study about pitot tube and orifice. So, pitot tube is also a device, a measuring device, okay, used for measuring the velocity of a flow at any point in a pipe or a channel. So, first to see this venturi meter and orifice meter were used for measuring the discharge, rate of flow. Pitot tube is used for measuring the velocity of flow. So, at any point in a pipe or a channel. And the principle behind this pitot tube is, it is working on the principle that if the velocity of a flow at a point becomes zero, the pressure is increased due to the conversion of kinetic energy into pressure energy. See, that means you have your water is flowing in this direction. So you have some velocity. So suddenly at a particular place, if the velocity becomes still, your velocity becomes zero. What happens? There is a conversion of energy. So the kinetic energy is converted into pressure energy in order to bring this velocity to zero, in order to bring the flow, that is the moving fluid, to a still fluid. So the kinetic energy is converted into pressure energy. So this is the principle behind the pitot tube. Now, see this pitot tube, it consists of a glass tube bent at right angles. So in the diagram, you can see this is a pipe. This is a pipe. This is a pipe through which our water is flowing. Okay. So we have water is flowing or the liquid is flowing in this direction. So the direction of a flow is this. This is the direction of a flow. And this tube is called pitot tube. So listen, the pitot tube consists of a glass tube bent at right angles. And the lower end, which is bent through 90 degree, is directed in the upstream direction. Now, what is called upstream direction? See, when you have a pipe or a tank or a channel or a dam, anywhere, if the water is flowing in this direction, see, when you are considering two sections, this is called upstream section and this is called downstream section. That means, see, water is flowing from this direction, right? If the water is flowing in the opposite direction, this will be called as the upstream and this will be called as the downstream. So, the lower end, which is bent through 90 degrees, directed in the upward direction. That means in the upstream direction. See, that means if your water is flowing like this 90-degree lower end should be directed in the upstream direction, towards, it should look towards the upward direction. So that you can see in the diagram. Okay, so this is your 90-degree pitot tube. The lower end is 90 degree. Lower end of the pitot tube is 90 degree and this is directed towards the upstream direction, right? This is our upstream because water is flowing from this here to here. So it is directed towards the upward direction, upstream direction. Now the liquid rises up in the tube. So the liquid rises up in the tube due to the conversion of kinetic energy into pressure energy. So when you are placing the Pitot tube, it is just a glass tube having 90° at the lower end. So when you are placing this tube, your water in the tube will, okay, your water in the tube will be up to this height. Now, what happens is there will be a rise of liquid level. Okay, so this rise in liquid level is taken as small h, and the depth of the tube in the liquid is taken as capital H. See, that means when you are placing a Pitot tube in this way, see, at this point, your velocity becomes 0. So, at all other points away from the tip of this tube, you will have some velocity. But at the tip of the tube, your velocity becomes 0. So what happens is, because this velocity is becoming 0 at this tip, the pressure at this point is increased, and due to the increase in pressure, there will be a rise of liquid in the Pitot tube. Okay. So the liquid rises up in the tube due to the conversion, and this is due to the conversion of kinetic energy into pressure energy. So suddenly at this point, the kinetic energy will be converted to pressure energy. So the velocity is determined by measuring the rise in the liquid tube. So you can measure this, what is this height, so that you can, with the help of this h, you can determine the velocity. Now, in order to determining the velocity, we are going to apply the Bernoulli's equation. Okay. So the liquid rises up in the tube due to the conversion of kinetic energy into pressure energy. Now we will consider 2 points. See, here we are not considering sections, we are considering points. We are considering 2 points, 1 and 2 at the same level, in such a way that point 2 is just at the inlet of the Pitot tube and point 1 is far away from the Pitot tube. Okay, so we will consider point 2 here. This point, we are considering 2 points. So the point at the inlet of the Pitot tube, that is closer to the inlet of the Pitot tube, we will consider as point 2, and at the same level, far away from the inlet of the Pitot tube, we will consider a point. See, these both should be at the same level. You are considering point 1. So let P1 be the intensity of pressure at P1 at point 1, P2 be the intensity of pressure at point 2, V1 be the velocity of a flow at point 1 and V2 be the velocity of a flow at point 2. Okay. So P1, P2, V1 is the velocity of flow at point 1, V2 is the velocity of flow at point 2. Capital H is the depth of tube in the liquid and small h is the rise of liquid in the tube. You can see the depth of tube and rise of tube. So capital H is the depth of the tube inside the pipe. So this is capital H, and small h is the rise of liquid in the tube above the free surface. This is small h. Now we will apply the Bernoulli's equation. So we will apply the Bernoulli's equation at point 1 and 2. So by applying Bernoulli's equation, we get P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Now, see, since the point 1 and 2 is taken at the same level, Z1 will be equal to Z2. So, what we get is, you can cancel this Z1 and Z2. Now, see, our assumption is because of the conversion of this kinetic energy into pressure energy, at the tip, that is at the inlet of the Pitot tube, your velocity becomes 0. That means your V2 is 0. See, that is our principle. If the velocity of flow at a point becomes 0, the pressure is increased due to the conversion of kinetic energy into pressure energy. So, here the velocity becomes 0 and there will be a rise of height. So, our velocity, this V2 becomes 0, right? So, now our V2 is getting 0. So, you can cancel this. So, remaining what we have is P1 by rho g plus V1 square by 2g is equal to P2 by rho g. Now, what is P1 by rho g? That is the pressure head at section 1. V1 square by 2g is the velocity head at section 1. P2 by rho g is the pressure head at section 2. Now, what is the pressure head at section 1? That is P1 by rho g will be equal to H. And P2 by rho g, that is pressure head at section 2, will be equal to H plus H. You can see here, you can see in the diagram. See, because of at this point, anywhere far away from this point, the pressure head is H. This is your pressure head H. This is your datum line. So, pressure head is H. At this point, your pressure head becomes, because the velocity becomes 0, the pressure head becomes H plus H. Okay. Now, we will substitute this H and H plus H in this equation. So, we will substitute P1 by rho g is equal to H plus V1 square by 2g is equal to capital H plus small h. So, from this we get, so you can cancel this H and H. You get H is equal to V1 square by 2g. So, from this we get V1 is equal to root of 2gh. So, velocity is equal to root of 2gh. And this velocity is called the theoretical velocity. So, V1 is equal to root of 2gh is called your theoretical velocity. Now, we know for the theoretical velocity, see, theoretical means we are assuming ideal condition. But actually, these velocities, for actual conditions, it is real, right? See, theoretical. When we are assuming and we do something theoretically, our assumption is ideal condition. The fluid is ideal. But in reality, it is real. So, ideal means it is non-viscous. There is no friction. There is no losses. Real means it is viscous. There is friction. There will be losses. So, in reality, the velocity will be less than the theoretical velocity. The discharge will be less than the theoretical discharge. So, now we will see what is actual velocity. So, in order to find the actual velocity, we will introduce a term called a coefficient called coefficient of velocity. So, our actual velocity, so V1 of actual velocity will be equal to CV, that is coefficient of velocity or coefficient of Pitot tube into the theoretical velocity. So, we get V actual is equal to CV into root of 2GH. Okay, what is a CV? CV is called the coefficient of velocity. See, this is one of the hydraulic coefficients, coefficient of velocity or coefficient of Pitot tube. Okay, So that means if you are using a Pitot tube, you can find the velocity at any point by using the formula Cv into root of 2gh. That's all. Now, how this h is measured? So we know velocity is equal to Cv into root of 2gh. So if it is root of 2gh, we need to find what is h. H is a small h, right? That is a rise of water, rise of liquid in the Pitot tube. Now, for finding the velocity at any point in a pipe by Pitot tube, you can have any of the following arrangements. See, this is our Pitot tube. Here, this is Pitot tube. So, everywhere this red color is Pitot tube, okay? Pitot tube. So, this is our Pitot tube. And here, this red color is our Pitot tube. Now, so we have 4 different arrangements. So, the first arrangement is, see here, this is our pipe, right? This is a construction line, continuous line. Okay. Now, so the flow of water is in this direction. This direction. This is our direction of flow of water for all the 4 pipes. Now, see the first case, you have a Pitot tube along with a vertical piezometric tube. So, this tube is called, we have already studied what is piezometer in your second module. So, this is piezometric tube. Now, there will be a difference in height here. So, this difference in height is small h, where h will be equal to so h is the pressure difference between the one minute. Okay, h is the difference in pressure head. Now, so how will you find h? You have already studied in the last class. H will be equal to x into Sg by, Sh by S0 minus 1 or x into 1 minus Sl by S0. That is, if the manometric fluid is heavier fluid, it is taken as x into Sh by S0 minus 1, and if the manometric liquid is lighter liquid, you have to take h as x into 1 minus Sl by S0. These things we have studied in detail in our last class. So, first case, it is a Pitot tube along with a vertical piezometric tube. You have a vertical piezometric tube. The second case, so again this is the direction of flow of a fluid. So, you have a Pitot tube. This is connected with the piezometric tube. See here it is used along with the Pitot tube. Here it is connected with the piezometric tube. So, when it is connected, your rise in the liquid level will be some point up to this, and here also there will be rise. So, this difference in height is taken as small h. Now, the third case, there will be a Pitot tube and a vertical piezometer tube connected with a differential U-tube manometer. Okay, so you have a Pitot tube, you have a piezometric tube, and this is connected to a U-shaped differential manometer. This is Pitot tube. This is piezometric tube. This is Pitot tube. These both are connected to a differential U-tube manometer. This is your third case. So that means, see, that there will be a difference in water level and the liquid in the manometer. So this difference is taken as H. Now the fourth case is, you will have a Pitot static tube consists of two circular concentric tubes, one inside the and other. So you have a Pitot tube and another static tube. See, you can see here, this is called another static tube, and these both the tubes are circular in cross section. One, the Pitot tube is inside the static tube, and these both, the outlet of these two tubes are connected to the differential manometer. See, this is the outlet of the Pitot tube is connected to the differential manometer. The outlet of this static tube is also connected to the differential manometer. Now, your difference in the liquid level will be like this. So, this difference is taken as small h. So, practically in this way, you will be in these four arrangements, using these four different arrangements, you can determine the velocity of the water flowing through a pipe or a channel. Normally, water flowing through a pipe. Okay, now we will move on to our next topic. So, already we have studied Venturi meter, Orifice meter. So, now we have studied Pitot tube. So, the formula for determination of Pitot tube is used for finding the velocity. The formula is Cv into root of 2gh. Okay. Now, we are going to study the next topic, that is Orifice. This is not a measuring device, but this is a part in your tank. So you will have a rectangular tank. You will have not a rectangular tank. You may have a tank where the water is flowing, and there will be a small opening in the tank. So this opening is called orifice. And with the help of the properties of this opening, you will be able to determine the velocity and the discharge. Okay. So this opening, the important thing is this opening is called orifice. Now let us see what is orifice. So it is a small opening of any cross section. So this opening can be any cross section, like it can be circular, it can be rectangular, it can be triangular, etc. On the side or at the bottom. So this opening can be at the side of the tank, or this opening can be at the bottom of the tank. Bottom also you can have an opening through which water is flowing. Okay, sometimes you can have the opening on the side. So from the tank the water will be flowing out. Sometimes you can have the opening at the bottom of the tank so that your water will be flowing like this. Now, how the orifices are classified? So, classification of orifices based on the size of orifice and the head of liquid from the center of the orifice. See, head of liquid from the center of orifice means this, if this is your orifice, so this is called center line of the orifice. So, if the water level of water is like this height is called head of liquid from the center of the orifice. Head of liquid, it is represented as capital H. Head of liquid from the center of the orifice. So based on this, based on the size of orifice or the head of liquid from the center of the orifices are classified into small orifice and large orifice. That means if the head is larger, if this head is larger, means orifice is smaller. You call it as a small orifice. If the head is smaller, that means your orifice is larger. You call it as large orifice. Okay, so if the head is small, that means if the head is large, that means head is greater than 5 times the depth of orifice. So this is the depth of orifice. If this head is greater than 5 times the depth of the orifice, then you call the orifice as a small orifice. And if this head is less than 5 times the depth of the orifice, that means if the head is reduced, you call the orifice as large orifice. Next, based upon the cross-sectional areas, your orifice is classified into circular orifice. That means this cross-section, okay, of this cross-section, the orifice is classified into circular orifice, triangular orifice, rectangular orifice and square orifice. Now, based upon the shape of the upstream edge of the orifice. What is upstream edge of the, I told you, see, upstream means your tank will be like this. Okay, your tank will be like this. So, your water will be flowing like this, right? So, see, this portion is called, this is called upstream and this is called downstream. Upstream and downstream. So, based on the upstream edge of the orifice, based upon this edge, it is classified as a sharp-edged orifice or bell-mouthed orifice. Okay, that means this part you can have sharp-edged or it can be sharp or bell-mouthed, curved. Okay, bell-mouthed orifice. Next, nature of discharge. How it is discharged. Okay, so you can have a tank. It can be drowned orifice or submerged orifice. So, submerged orifice can be fully submerged orifice or partially submerged orifice. So, drowned orifice normally comes at the bottom. Submerged orifice normally comes at the side and it can be fully submerged or partially submerged. So, these are the classification of orifices. So, totally 4 classifications based upon the head of water, cross-sectional areas, shape of the upstream edge and the nature of discharge. Now, we will find the velocity. See, same way as you studied the Pitot tube. So, now we will consider a tank. You can see the tank here. So, you consider a tank which is fitted with a circular orifice in one of its side. So, you can take the cross section of the orifice. You assume the cross section of this. So, this is the orifice. You assume the cross section of the orifice is circular. Now, let capital H be the head of the liquid above the center of the orifice. So, this is the center of orifice. Okay, this is the center line of the orifice. So, this is our water level. Okay, water level. So, this distance of water level, free surface of water from the center line of the orifice is taken as capital H. Now, the liquid flowing through the orifice, it forms a jet of liquid whose area of cross section is less than that of the orifice. That means, see, when you open this orifice, the water from the tank flows out. So when this water is flowing out, it forms a jet of liquid, and the area of that jet will be less than that of the orifice. That area will be less than that of this area. See, that means from this, see, water will be rushing like this, right? So from this, your water will be moving like this. It forms a jet, and after this it gets spread. See, it is in this way how your water will be pushed out. So the liquid flowing through the orifice forms a jet of liquid whose area of cross section, see, from this point, from this to this point, the diameter is getting decreased, and after that it gets increased. So the area of cross section gets decreased from this point to this point, and then it gets spread, so increased. Now the area of the jet of fluid goes on decreasing at section CC. That is, the area is minimum. That is at a distance of approximately half the diameter of the orifice. So see, this circular cross section. So you have a diameter of this orifice, right? So up to a distance of half the diameter. So it is assumption, okay? So up to CC. That means the lowest cross section area, we take the section CC. So this section can be taken as CC, and this distance is approximately taken as, this distance where you have the lowest cross section is taken as D by 2, where D is the diameter of the orifice, approximately equal to half the diameter of the orifice. That means, see, at a distance equal to half the diameter of the diameter of the orifice, you will have the lower, smallest cross section area for the jet. So that section is taken as CC. Now, okay, so at a distance approximately equal to half the diameter of the orifice, you are considering the section CC because there the cross section area will be minimum. So at this section CC, the streamlines are straight and parallel to each other. Okay, so at this section, the streamlines are straight and parallel to each other. So listen, see, from this up to this it is decreasing, and for a small region the streamlines will be straight and parallel, and after that it will be diverted. So converging, straight and parallel, then it will get diverted. Okay, and perpendicular to the plane of the orifice. So this is your plane of orifice, and this streamlines will be perpendicular to the plane of the orifice. Okay, see, this is your plane of the orifice, and the streamlines will be perpendicular to this plane of the orifice. Now this section is called vena contracta. Always, see, in the orifice meter also you have studied the smaller area is called the vena contracta. So here also this section is called vena contracta. So now this section CC is called vena contracta. Okay. So beyond this section, the jet diverges and is attracted in the downward direction by the gravity. So what happens is, beyond this, it will be diverted, and after that, by gravity, this will be falling downwards. So this is the principle behind the orifice. Now let us see the derivation. We will consider 2 points 1 and 2. So we will consider 2 points 1 and 2. So 1 we will consider at a distance far away from the orifice. So we will consider 1 at this point. And the point 2 is taken at the vena contracta. Okay. So we are considering 2 points. Point 1 inside the tank, some distance away from the orifice, and point 2 is at the vena contracta. Now we are assuming the flow is steady and at a constant head h. So the water level in the tank is maintained at this level h. Okay, so the head is maintained. The water level is maintained as capital H. For this height, the water level is maintained. Now we will apply the Bernoulli's equation. So we are applying Bernoulli's equation at points 1 and 2. So we know Bernoulli's equation is P1 by rho g plus V1 square by 2g plus Z1 will be equal to P2 by rho g plus V2 square by 2g plus Z2. Now, this is 1 and 2 are taken at the same level. So, Z1 will be equal to Z2. So, you can cancel that. Now, this head is equal to the pressure head at point 1. That is, your P1 by rho g, pressure head at point 1 is H, because that is the height of the fluid inside the tank. So that is H. That is the pressure head. So you have already studied the intensity of pressure P will be equal to rho g H, right? H is the head. So head will be equal to P by rho g. Pressure head will be equal to P by rho g. Intensity of pressure is rho g H. Okay. Now, what is P2 by rho g? See, at vena contracta, your height will be very minimum. Almost approximately equal to 0. So, we will consider P2 by rho g will be equal to 0. Because here it is atmospheric pressure. At atmospheric pressure, the pressure head will be equal to 0. Now, this V1, see, you have V1 and V2, right? So, this V1 will be very, very small when compared to V2. The reason is our assumption, we assume that the area of tank is larger. For greater area, for large area of the tank, we are maintaining this constant head. We are maintaining this head of water. That means the velocity at 1 will be very less when compared to the velocity at 2. So, if that is the case, velocity at 1 will be taken as 0. Will be approximately equal to 0. So, velocity at 1 will be approximately equal to 0. So, we get P1 by rho g. So, P1 by rho g is taken as H. So, H V1 square. V1 is taken as 0. So, H is equal to this P2. Pressure head is 0. So, H is equal to V2 square by 2g. So, from which we get V2 is equal to root of 2gh. This is nothing but the theoretical velocity. So, what will be the actual velocity? The theoretical velocity will always be greater than the actual velocity. So, actual velocity will be equal to Cv into the theoretical velocity. So, V actual is equal to Cv into root of 2gh. So, the formula is same. The formula is the same. Capital H. It's not small h, small capital H. Okay. So now you can compare and study. See, I hope you remember the formula for Venturi meter and Orifice meter. That is, discharge is equal to CD into A1 A2 by root of A1 square minus A2 square into root of 2GH. Here for velocity, velocity is equal to CV into root of 2GH for the case of Pitot tube and Orifice. So compare and study, that will be easy for you. Now we will see the hydraulic coefficients. So we have three different hydraulic coefficients. So you have already studied this: coefficient of velocity, coefficient of contraction, and coefficient of discharge. So first of all, let us see coefficient of velocity. We have three coefficients. Okay, first is coefficient of velocity, CV. So CV, coefficient of velocity, is defined as the ratio between the actual velocity of jet at vena contracta and the theoretical velocity of jet. So CV is equal to actual velocity of jet at vena contracta by theoretical velocity of jet. See, because actual is always less. Okay, actual is always less than theoretical. Always remember this. So actual will be equal to some coefficient into theoretical value. Actual velocity is equal to coefficient of velocity in theoretical value. Actual discharge will be equal to coefficient of discharge into theoretical discharge. And this coefficient value will always be less than 1. So remember this concept. So our CV is equal to, see, actual velocity is taken as V, and the theoretical velocity we have determined it as root of 2GH. So CV is equal to V by root of 2GH, where V is the actual velocity and the root of 2GH is the theoretical velocity. And this value of CV, I told you, it is always less than 1. CV or CC or CD, coefficient of velocity, coefficient of discharge, and coefficient of contraction, always less than 1. So CV, coefficient of velocity, the range is between 0.95 to 0.99 for different orifices. It depends upon the shape, size of the orifice and on the head under which the water flow takes place. And generally, the value of CV is taken as 0.98 for sharp-edged orifices. General case, if the value is not given, you can take it as 0.98 while solving the problems. Okay. Now, second coefficient is coefficient of contraction. So, coefficient of contraction is the relationship, the ratio between the areas. Ratio between the smaller area and the larger area. See, velocity, you see ratio between the smaller velocity by larger velocity. So, numerator is smaller, denominator is larger. Smaller velocity by larger velocity. Here the smaller area by larger area. So, CC, coefficient of contraction, is equal to area of jet at vena contracta. Vena contracta is the smaller area divided by area of the orifice. So, CC is equal to, coefficient of contraction is equal to AC by A. AC is the area of the jet at vena contracta and A is the area of the orifice. And the value of CC is normally taken between 0.61 to 0.69 depending upon the size and shape of the orifice and the head of the liquid under which the water flow takes place. And in general, the value of CC can be taken as 0.64. Similarly, the coefficient of discharge also, see, smaller value, smaller discharge by larger discharge. The theoretical is always larger. Actual is always smaller. So, coefficient of discharge CD is defined as the ratio of the actual discharge from the orifice to the theoretical discharge from the orifice. So, actual discharge from the orifice divided by theoretical discharge from the orifice. So, CD is Q actual by Q theoretical. So, Q actual is nothing but actual velocity into actual area, and Q theoretical is nothing but theoretical velocity into theoretical area. So, you can write it separately: actual velocity by theoretical velocity multiplied by actual area by theoretical area. What we get is, see, actual velocity by theoretical velocity is the coefficient of velocity CV. Actual area by theoretical area is the coefficient of contraction Cc. So we get Cd is equal to Cv into Cc. Very, 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 very important. Now CD, the coefficient of discharge is taken between 0.61 to 0.65. That is approximately equal to 0.62. So that's all for today. The next class we will study about the experimental determination of hydraulic coefficients. So for all these hydraulic coefficients, how will we determine the hydraulic coefficients experimentally? Then we have to study the flow through large orifices, that is discharge through large rectangular orifice, discharge through fully submerged orifice, then what is the time required to emptying the orifices, etc. So that we will see in the next class. Thank you for today. So remember what we have studied so far are for Venturi meters and for orifice meter. The discharge is equal to CD into root of A1 A2 by root of A1 square minus A2 square into root of 2GH. See, for orifice, this A2 is represented by AO, area of the orifice. For Venturi meter, A1 is the area of the pipe and A2 is that is area of the inlet and A2 is the area of the throat. For orifice, A1 is the area of the inlet and AO is the area of the orifice. Now for Pitot tube and for orifice, V is equal to CV into root of 2GH. And here CV into root of 2GH for orifice. Okay. So remember these things. And the hydraulic coefficients are CV, coefficient of velocity, CC, coefficient of contraction, and CD, coefficient of discharge. And CD is equal to CC into CV. So these are the things we have studied so far. Then we have studied the Bernoulli's equation. Before this, we saw how to derive the Bernoulli's equation from Euler's equation by assuming the streamline flow from streamline. Okay, thank you. Thank you for today.